Hello, class. This is week 12, and we put three things together: optics, heat, and fluids. And so hopefully this won't be too confusing, but I think it'll be okay. We'll talk about optics, and optics means lenses, which enable you to make telescopes and microscopes. Optics also explains rainbows and color. Okay, so that's one whole topic. Heat engines are remarkable. I mean, your gasoline engine, your car engine is a heat engine. And there are many, many other examples of heat engines. In fact, your human body is a heat engine, in fact, in a general sense. They're amazing devices. You simply put a little heat in there, and a motor starts to run, or something starts to work, okay? And you need a temperature difference. You need a temperature difference and some heat, and that's all. And finally, there's fluids. Now, fluids, actually, if you think about fluids for a minute, they're vastly important. I mean, there's air and water, and there's pressure, and there's various principles like Bernoulli's principle. But, you know, your whole body is filled with tubes and vessels that carry fluids, both air and blood and other fluids. And the Earth, as a whole globe, is even more remarkable. There are fluids all over the Earth. There's winds of all different kinds swirling around the Earth. There are oceans, deep oceans and shallow oceans, and the cold water goes down beneath, and the warm water goes over the top, and huge transports of energy take place in the fluids of the Earth. So they're wonderful topics. Okay, so let's just start right away with optics here. Here is a beautiful double rainbow. You can see the main rainbow here. It's quite obvious to the eye, but if you look outside of that, you'll see the other rainbow, the second rainbow. And the rainbow happens when you have a large field of raindrops, and we can call them spherical. They're not really spherical, by the way, but call them spherical. Sunlight comes in from the left-hand side, the back side of you, by the way, and then it refracts at one surface. It travels through the inside of the raindrop. It reflects from the back surface of the raindrop, reflects and goes down, and then refracts again, coming back out. So if you look at, for example, 42 degrees down from the horizontal, 42 degrees down from the horizontal, that's the angle at which you'll see the rainbow light coming into your eye. Okay? So we won't go any further into rainbows here, but it all comes from sunlight. I mean, this light that's coming in from the left on the raindrop is actually sunlight. It's white light, all right, by definition. So sunlight is defined to be white light, and if you take a look at its spectrum, and you did this already with the diffraction grating, you can do it again too, you'll see that at the low energy end, it's infrared, then the near infrared, and then in the middle there's the visible light, which goes from red to orange to yellow to green to blue to violet. That's all the visible range, and it's called visible because our eyes detect that light. They don't detect stuff outside of that band. That's what we see, and that's all we see. And then above that there's the ultraviolet and the A, B, and C bands. And so, for example, the C band of ultraviolet is actually very high energy light, and it actually gives you skin cancer if you get too much of it. Then there's another, giving names to all this. Now here, the entire spectrum of light, that is to say electromagnetic waves, is in the bottom left-hand corner, and they're labeled by the names we've given to them. And you'll notice that narrow thing in the middle is actually the visible range. That's the visible, and it goes in, and it goes from the violet to the red, and you notice it's reversed. The upper right hand figure is in terms of energy, and lower right is in terms of wavelength. And the higher the wavelength, the lower the energy. Okay, so at very, very low wavelengths or high energy, we have sort of called cosmic rays. Gamma rays, X-rays are in here. When you get a dental X-ray, that's the wavelength of light that's being sent through you. And then there's ultraviolet, and then the visible, infrared, far infrared, and then there's radar, ultra high frequency and very high frequency, shortwave and radio. Okay, so all of these things basically are the same thing, just different energy, and therefore different wavelengths. So optics only deals with the stuff we see with our eyes. Okay, so for example, the first fundamental principle of optics is refraction, and refraction happens, for example, when you have this blue material, which could, for example, be glass, and up above it there's air, so it's air glass, and the air, and you can characterize all optical media by what's called the index of refraction, a little n. And so the index of refraction of air, or vacuum, is N1, which is just equal to 1. And the index of refraction of glass, in this figure labeled N2, is something like 1.5. Okay, typically 1.5. Water has an index of refraction of 1.33. Okay, so if a light ray comes in from point Q, so the red ray is a light ray coming in from the air going into the glass, it bends. And that bending angle is called refraction. So the angle theta 1 is the angle that it comes in with respect to the vertical dotted line, which is called the normal, okay, perpendicular to the surface here. And you can see that theta 2 is smaller than theta 1. So light coming in off the normal from a low index to a high index material always refracts towards the normal. Okay. That's called the principle of least time. It's called refraction. There's a formula for it called Snell's law, but we're not going to bother with that. The important thing about the principle of least time, it tells you the light goes in both directions. So if you start the light out at point P, it'll bend outward when it goes into air and end up at point Q. Okay, and that's refraction. This is the basic simple principle upon which all lenses and telescopes and microscopes are based, including the rather remarkable lens in your cell phone. By the way, your cell phone camera has an absolutely remarkable lens in it that takes images from both near and far together. I'm not even sure how it's done, but it's very remarkable. Well, now by shaping the surface of the glass in just such a way, you can create a simple lens. And so this blue is a lens, and you can see this is called a convex lens. And if you have an object here at position O, and it's like an object can just be an arrow, and this could be, for example, a lighted sign or something, or it could be a candle or something, but that's the object. And the object gives off light. So it gives off light in all directions, but in particular, it gives off a ray of light that goes horizontal, and then when it enters the glass, it refracts once, it comes out the other side, refracts again. The total refraction angle goes down through the point labeled F, and that's called the focal point. And then it just keeps on going, okay? And then there's another ray. You can always draw 3 rays, and here's 2 of them. There's another ray that comes from the tip of the arrow, and it goes directly through the center of the lens. So it refracts a little bit on the coming in, a little bit on the way out, and they cancel. And it keeps going through again, keeps going straight through. Where these 2 rays meet in space, that is where the image is formed. If you look at any place else, you get a fuzzy image of this object. But if you're just at this point, that's where the image forms, and you get a nice sharp image. Okay, so this is a simple lens. Okay. Now you can always draw these 2 rays. Okay, they're called it's called ray tracing to do that. So now let's look at the focal length of a lens, a simple magnifier, and a 2-lens microscope. So inside of your packet there are a couple of very cheap plastic lenses. I apologize, I could not get decent glass lenses for this course. So here we go.
Okay, we're going to look at lenses. Now these are 2 extremely cheap plastic lenses. I apologize, I could not get my hands on good glass lenses. So these are just simply 2 plastic, and you'll see the quality is terrible. But the first thing you can do with the lens is measure its focal length. So there's a light up on the ceiling, which is kind of far away, and you can see that as I move this back and forth, this The focal point here is very diffuse. It's not very clear. Here it's also diffuse. Right here where it focuses the best, this is the focal length. So from right here on the paper to the lens, that's the focal length. It's like, 7 inches or something like that, okay? So that's one lens, that's a small lens. The other lens is about the same, a little bit, slightly longer focal length, but you can see the focal length is about this much, and maybe it's like 9 inches, say, or something like that. So they don't differ very much from each other. Well, the first thing with a lens is you can do what is called a simple magnifier. So here's some lettering, and for example, I'll put this here, and you can see that it magnifies, right? That's a simple magnifier. The letters are about 2 times, maybe, or 3 times bigger. Okay, it's an upright magnifier. 2 lenses together, you can make a compound microscope. Let's see how that works. One here and one here. And if we adjust the distance between the two like this, you can see, there you go, there's a microscope, okay? Maybe 5 times, magnification of maybe 5 or something like that, okay? So now, with good lenses, you could do a much better job here of a compound microscope. Okay, so I'll describe more then in the recorded lecture.
Okay, here's the optics for a simple magnifier. Now, don't get scared by all the lines. On the left, you see there's an object. It has a green top and a red base, okay? And then there's a lens, a so-called convex lens. It's a magnifying, focusing lens. And then here's your eyeball sitting here. And then, so let's take, I'm sorry, here. The object is the small thing with a green top to it. And that gives off light, and they're the same 2 rays of light. One that goes parallel to the axis, the dotted line here is called the optic axis, parallel to the axis. It refracts and goes down through the focal point into the eyeball, and then the other ray goes through the very center of the lens and just keeps going straight again into your eyeball. Now these 2 rays, they both come from the same point, and your brain puts these 2 rays together and forms an image. And the image is clear and sharp where these 2 rays that go into your eye extrapolates them backwards to where they meet, and they meet here at the image. And so you can see the image distance is farther. The image is farther away from the lens than the object. There are 2 things that are important about this. One, the image is bigger than the object. Here it looks like about 3 times bigger. So the magnification of this lens is about 3 times larger. The second thing important is that it's upright. In other words, it's the green is on the top, the image is upright just like the object, and so it's an upright image. So this is the same thing we did with a simple magnifier looking at the print in a magazine here. Okay? This happens when the object is inside the focal length of the lens. So the focal length of the lens we were looking at was like 9 inches, but we held it only 3 or 4 inches away from the page. And so we saw an upright, enlarged vertical image. All right? Now, here's 2 lenses. This is actually a telescope, a 2-lens telescope. It gets a little more complicated here, okay? Now, again, for a telescope, your eyeball is on the right-hand side here. The eyepiece lens is what you look through. It's a little lens with a short focal length, and FE is the location of the focal points of the eyepiece lens. And then there's a big objective lens, which has a long focal length, like maybe a foot or 2 feet, okay? And then the focal length of the big lens is F sub O for objective, okay? Now, how does it work? Well, you have in the far, far distance, you have a campanile, a tower here, okay? And the rays that come in from very far away are almost parallel because they're coming from something very far away. And again, there are two rays here, one which goes directly through the middle of the lens, it just keeps going straight, and the other one that goes through a part of the lens, and then the focal, and then because it comes from far away, the lens bends it into a ray which is parallel. Those 2 those two rays now come together at approximately where the focal length of the lens is, all right? Because the rays came in from infinity, so it's they have to come together at the focal length now. So this is the image of the object. And then the two rays continue on, and they are bent, refracted even more by the eyepiece lens, and those two rays get refracted up into your eyeball. And so your eyeball now sees these rays coming in, extrapolates them back, and they come together. At some point, you know, if the objective lens is, say, 3 feet away, then this image gets formed about like 2.5 feet away from you. In other words, that tower in the distance now looks like it's right in front of you, okay? And you see this large, inverted, upside-down image in your eyeball, okay? That's the way a telescope works. Now, if we had two lenses, for example, one that had a focal length of, say, 50 centimeters, and another one that had a focal length of 5 centimeters, then we would be able to make, just by holding them in your hands like this, we would be able to make a relatively decent telescope with a magnification of 10, because it's the focal length of one divided by the focal length of the other. That's the magnification. So we won't be doing this, but in a regular classroom lab in this course, we would easily make these telescopes with a large variety of lenses around. Okay, that's a telescope. Now, what's this two-lens microscope? How did that work? Well, you have, again, you have an eyepiece lens, which you look through with your eye, and there's an objective lens. And these two don't have to have a widely different focal lengths. Similar focal lengths also work, as you saw. We saw like a magnification of 5. So here's the object on the left-hand side, and then there are 3 rays. There's the one parallel to the axis, the one that goes right through the center, and then there's another one that goes through the focal point and into the lens, and that one must come out parallel to the axis. Okay, so they all meet here at the so-called first image, and then they continue on, and they're all refracted by the eyepiece lens, which goes into your eyeball, and your eyeball sees an upside-down image of the small object. Okay, so it's like a telescope, except the scales are a little bit different and the lenses are different. But again, you can hold. This is exactly what we did with our two little cheap lenses. We just held two lenses together, and you can see the distance apart is going to be something like twice the sum of the two focal lengths plus a little bit, and so on. And we saw an upside down image. Was it upside? It wasn't upside down. It was right side up. Well, in any case, I know why, because we were inside here. In any case, this would make a good microscope. Now, in a lab, for example, or in a classroom, you want to have something that's lighted. So one thing you can do is take a regular table lamp, a little lamp, and put an aluminum over it and cut out an arrow. So now you have a bright arrow that you can now look at to make a telescope and look at this light, or you can use this light far away to get the focal length of any lens. Okay. Well, now this is also something too. This is a so-called light box, just a plastic box, and you have 3 green lasers shining light in from the right-hand side, and there's a objective lens here, and an eyepiece lens, and you can see the focal point. So all these parallel green laser beams come together at one point. Okay, you have to fill this box with a little bit of smoke, and that's the only reason why you see the lasers, because it scatters off the smoke, and then you see it with your eyes. If this were just air, you might not even see the beams. Okay. All right, so now here's all of lenses and mirrors. They all go together in one formula, but we're not going to go into great detail with this. You can look up optics, and this is called the thin lens formula here. O is the object distance, I is the image distance, and F is the focal length of the lens. So here's a converging lens. Light comes in from the left. Parallel rays come in from the left, in other words, from some source far away, and they cross right at the focal point, and little f is the focal length. All right, so that's little f in the formula here. A diverging lens, the light comes in from the left-hand side. And you can see it's a diverging lens, so-called concave lens, and the light refracts outwards instead of inwards. Okay, And if you trace those rays backwards, they meet at a point, and that's called the focal length of this lens. In a diverging lens, the focal length is still the focal length, but it's a negative number. So this might, for example, be minus 10 centimeters. Okay. Whereas for the converging lens, the focal length would be plus 10 centimeters. And that makes a difference when you put it into the thin lens formula here. Now there's the mirrors. There's the concave mirror, and light comes in from the left, reflects from the mirror, and meets at the focal point. Okay. And for a so-called convex mirror, the light comes in, bounces out, bends out, reflects outwards, trace them back in by the dotted lines. It meets at the focal point, and that's called the focal length. So this would be a negative focal length for a mirror. So if you put any object at a distance O from the lens or the mirror, it would form an image at distance I away, given that your lens has a focal length of f. So this little formula works for all of these cases. So if you ever have to design something or figure something out, that's the way to do it. All right, so now there's a thing called total internal reflection. That is to say, when there's a light ray inside of, for example, water, air outside, the water is coming out at the surface at an angle theta 1 with respect to this dotted line, which is called the normal, and it refracts out. But at some angle theta sub c, which is the critical angle, the light doesn't go outside anymore. It goes right along the surface. And for any little angle bigger than theta c, the light is totally internally reflected inside the water. All right? Now, if this water, for example, were a plastic fiber, this is the way the internet signal is passed around the ISU campus. It's passed around in a fiber, a plastic fiber, with the light, the internet signal being a series of light bursts, is totally internally reflected, so you don't lose any light. It's a really remarkable thing. And then here's again an optical illusion. The refraction of water, index of refraction of water is 1.33. And you can see the photograph on the right. It looks kind of funny. Well, it's only because it's refracting. If you put a pencil in here, the light that leaves the end of the pencil at point X goes up and refracts at the surface and goes into your eyeball. Your eyeball believes that the end of the pencil is at point Y because that's where you see it, all right? But it's really at point X. So that's refraction. You can always do this in a classroom, okay? Well, there's a Fresnel lens, and I didn't pass out Fresnel lenses, but in any case, a Fresnel lens is, how do you make a huge lens? For a lens, for example, that's say 2 feet in diameter, if you made it out of glass, it would be pretty heavy. But if you cut it, the plastic like this, like at the lower thing, you can get the same optical effect of focusing at a point with a Fresnel lens, and it's just a simple, millimeter thick piece of plastic. So here's an image, for example, of looking through a Fresnel lens. Well, now a prism, I guess let's not do too much about prisms, except you put white light into a prism. It refracts at one surface, and the blue light, having a shorter wavelength, refracts more than red light, and so they separate. And then coming out the other side, they refract even more. So you spread the light out from red to green from blue to green to red. Okay, and that's what a prism will do. So in a prism, you can see here's the white light going into a prism, and you can see the spectrum coming out. Okay, so that's a little bit of optics. Now, a discussion of heat and heat engines is a beautiful subject. But first off, remember one essential fact is that the heat is actually also kinetic energy. In other words, all the molecules, they have each one has a small mass, but there are a lot of them, and they bounce around, okay? And the kinetic energy of those molecules is measured by measuring the temperature, okay? So what's temperature? Well, we have on the left-hand side, we have the Fahrenheit scale. Fahrenheit scale has two important numbers. One of them is 32 Fahrenheit, that's when water freezes, and 212 Fahrenheit, that's where water boils. And Mr. Fahrenheit is the one who established this scale. It's the British scale unit. The much more interesting one is the Celsius scale, where freezing is 0 degrees and boiling is 100 degrees. So that's much simpler. But all temperatures in any physics formula are always also in the Kelvin scale, and that's on the right-hand side, the Kelvin scale. Because you think about it for just a minute here. Since temperature measures kinetic energy is 1/2 mv squared, and m is always positive, and v squared is always positive. So a kinetic energy can never be negative. Well, you notice on Fahrenheit and the Celsius scales, very down at the bottom, and they become negative degrees, okay? Well, kinetic energy can never be negative. So the Kelvin scale pegs zero kinetic energy at 0 Kelvin. And that's given a name of absolute zero. You can never go lower than that in temperature. It's absolute zero. And then in which case water freezes at 273 Kelvin and boils at 373 Kelvin. Okay? So this is the physical scale. All right. Now, so heat. How do you get heat from one place to another? For example, suppose you have a metal bar, and one end of it is hot and one end is cold. How long will it take for the whole bar to become warm? Well, that's so-called conduction. Conduction happens when atoms and molecules, the hot ones, have a high kinetic energy. Even though they're a solid, they're still jiggling around even more, even in a solid, because there's still kinetic energy goes with temperature. So the atoms and molecules are just banging against the nearby atoms, transferring their kinetic energy to the next atom along the line. Well, so I did an experiment. Here. I took a butter knife, ordinary butter knife, and I put one end of it on my kitchen stove. It's a gas stove, so there's a flame. So it heated up this end of the knife. Quite hot, actually. You could see it becoming red hot. Okay, it was quite hot. And then I put my finger on the other end of the knife to see how long it would take the heat to travel from this end of the knife to my finger. Well, I held it for a long time, and the end I was hanging on was still cold, even though the other end was red hot. So I just let it sit there without do other things, right? Okay. So after 12 minutes, I have 12 seconds here. After 12 minutes, my God. After 12 minutes, the other end became warm. Only warm, not hot. So this is called conduction. Heat will transfer from one place to another place by conduction. In other words, atoms banging against the nearby atoms. Very, very slow process, conduction. Now, I warn you, you don't have to do this. I warn you, you will kind of basically ruin a butter knife. So you could, any piece of metal will work, by the way. Actually, I didn't think about this, but our ruler would also work. Okay, but conduction is very slow. The other way to transfer transfer heat, is with radiation. For example, ultraviolet. That means the energy, heat gets from the sun to the earth by radiation. It's just light coming across empty space. A campfire, a radiant heater. These are all heat transfer by radiation. But you have to have an open space because the radiation can't bump into anything on the way, right? So now, and the third and only way to transfer heat is by convection. And convection is how every building, every home is heated. So wherever you are now, the way you're heated is that somewhere you heat up, basically air, usually heat up air, and then you pump it through tubes that go all the way through the building or the house. That's called convection. It's very efficient, very fast. Okay, so you're just blowing hot air around. Okay, so that's convection. Now heat engines. This is let me describe, because heat engines are everywhere. A steam engine is a heat engine. Your automobile engine is a heat engine. Okay, they all have the same basic principle. They're really amazing, but they're not easy to build. Okay, so we've never built one actually in this course. You have at the top, for example, you have a heat source at some high temperature, TH. It's a hot source. This may be, for example, the burning fuel inside the cylinder of your automobile, for example. And that's where the money comes from. You pay for that. You pay for that hot source. And then a certain amount of heat is taken out of that so-called hot source or reservoir as some Q, which is so much energy. And that Q gets divided into two parts. One, it produces work. In other words, it makes the shaft of your engine turn around so that your car goes, right? So that's what comes out as W, and that's the actual work done by the engine. But there's some fraction of it, Q sub L, heat that gets put into the so-called cold sink. In other words, it's waste heat that comes out the exhaust pipe of your car, for example, or it heats up the block of the engine, for example, and just radiates away or conducts away. So that's called waste heat. So a heat engine always starts out by putting energy in as something hot. Waste heat comes out at some lower temperature, and some fraction of the incoming energy does actual work. Now, the actual work done, you can ask how much work do you get for how many dollars you put into your hot source, your heat source. And the answer is, for example, an automobile internal combustion engine, the efficiency is about 25%. So W is only 25% of QH that comes out of the heat source. A Stirling engine is more like 40%. Okay? So heat engines are never terribly efficient. But now here's some examples of some fun heat engines, toy engines. Here's a soda can hanging from a swivel, and you put a couple of holes in it, and then you have a Bunsen burner underneath. You boil the water, the steam comes out the holes, can starts spinning around. It's a heat engine. Upper right hand is a thermoelectric heat engine. You put hot water in one beaker and cold water in the other beaker, and it generates a voltage, just like a battery. It generates a voltage. The voltage runs a motor. The motor turns a fan. Okay? You're turning heat into electric energy directly. That's called a thermoelectric engine. And then there's the dipping duck engine, more complex to describe, but basically the dipping duck stores energy gravitationally, and then its nose gets wet, and when by the just room temperature water here, and then the duck goes back straight up again, and then the water on the nose of the duck evaporates, and evaporation leads to cooling, so that the head gets cold and draws water up, which tilts the gravitational balance, and it dips its nose in again. All right, so that's also a heat engine. Okay. Here's again another one of another heat engine. You boil water, drive a piston, you do work. Okay, that's a heat engine. These are actually Stirling engines. 40% efficient. Really rather beautiful devices. You just light a candle under the hot end, and then there's a cool end, and this one piston goes back and forth and rotates the shaft, and it's actually quite nice. Okay, quite nice. Well, there's one other thing that heat does, is that when any material is the temperature of it is raised, is heated up, it expands, becomes longer. Okay, and if you've ever seen a large bridge, like a bridge over the Mississippi River, it has these so-called expansion joints, because the whole bridge may be 1,000 feet long, but between winter and summer, the bridge will get longer or shorter by something like a foot. So you have these expansion joints. During the summer, it heats up, it expands, and the joints do this. And during the winter, it shrinks down and it does this. But year-round, a car can drive over the top of it, and the bridge does not break. Okay. Lower right is a 1/4 inch every 50 feet on the railroad rails. If you go out and look at the railroad rails going through Ames, you'll see these little 1/4 inch gaps. And that's meant so that during the summertime, the iron expands and this closes up, and during the winter, the iron gets shorter, shrinks, and this expansion joint expands. Okay? So now, the reason for that, by the way, is the same reason we found that, a ruler like this will flex. It'll flex up and down because, like the atoms, the iron atoms are like connected by springs, and the average distance between the atoms depends upon the temperature. And so the little figure at the right shows the same potential energy function as a function of the separation of the two atoms. And they're at low temperatures, the energy E1, they kind of jiggle around at the usual place. But you warm them up, they jiggle farther out. And warm them up, they jiggle even farther out. And so the average separation gets larger as the temperature goes up. And that's why all materials expand. Now, there's nice ways to do this. I hope someday in a classroom, for example, you may have access to liquid nitrogen or dry ice, and maybe a caliper to very accurately measure the length of a metal bar, like aluminum or even PVC actually will work. Then there's a digital thermometer here, not too expensive, and you can easily measure the temperature. Here's an aluminum bar, and here's a copper, I guess a brass tube or something like that. So you can actually measure the length. You can actually measure the length of an object with a caliper as a function of the temperature, and you'll see that you may start it out, for example, put it in dry ice to begin with, measure it, and then just let it sit there, and it'll slowly expand as the temperature goes up to room temperature. So that's thermal expansion. Okay, so now that's all kind of useful and nice. Let me tell a small story about thermal expansion. You know, when you have a delicate thing like, for example, a computer, or maybe it's electronics that's on a Mars rover or a moon lander or something, and you go from, say, high temperatures during liftoff, for example, down to very, very cold temperatures in outer space. So whatever you build, whatever mechanical things you build, whatever computer chips you have that may have gold contacts in them and so on, you have to account for the fact that they will thermally expand and contract under temperature. And once there was a, very expensive piece of scientific equipment in which the engineers in charge of designing it, they neglected to consider thermal expansion. And of course it expanded and it shrunk under the cool of space, shall we say, and shorted and stopped working. Okay, so even small things like thermal expansion, a good engineer gets all these things right. You just don't miss a single thing, right? Okay, so now let's jump to fluids. Finally, fluids. For example, here's the Earth down here, and there's an atmosphere of air, mostly nitrogen and 20% oxygen, and this atmosphere is about 100 miles high. After you get above 100 miles, there's not much left, okay? And it's more dense at the bottom than it is at the top. Now, this atmosphere, by all these molecules, are kind of hugging the surface of the Earth because of gravity. Gravity is attracting the molecules to the Earth, so they all hug the Earth. Okay, down at the bottom, it's more dense, all right? If you were to take 1 square inch on the Earth's surface and take a 1 square inch column all the way out to space, if you weighed how much air was in that volume, in this square inch tube, it would be 14.7 pounds. Okay, 14.7. If you were just to take that much air and put it on a scale and weigh it, 14.7 pounds. So at the surface of the Earth, so-called atmospheric pressure is 14.7 pounds per square inch. That's it. And it has entirely to do with the mass of air and the gravitational attraction. In other words, mg, the gravitational attraction of a mass to the Earth at the Earth's surface. All right. So that's where atmospheric pressure comes from. It comes from the gravitational weight of the air above you. Okay. Now, same thing works for water. Suppose you have a surface of water here, and say the pressure is 0 there. I mean, atmospheric pressure it would be actually. Every distance, you go underwater now. You go underwater at distance d. Okay. The pressure increases to the density of the water times the gravitational acceleration, which gives you the force, times the depth d, because the depth measures how much water there is above you. If you go down 10 meters, you pick up 1 more atmosphere of pressure. In other words, you pick up another 14.7 pounds per square inch. And you go down 20 meters, you have twice that. You go down 30 meters, and you have 3 times that. Okay, so you have 3 additional atmospheres of pressure on top of the air on top of that. So the Earth has one fluid on top of another fluid. It has an air fluid on top of a water fluid, okay? And they all have they all go from pressure 0 in outer space all the way down to the surface, which is 1 atmosphere of air pressure, and then you go underwater and you simply add on, for every 10 meters down, you add on another atmosphere of air pressure. So that's where pressure comes from, okay? Now, buoyancy is familiar. Boats float, after all. And the simple rule is that buoyant force up is equal to the weight of the water you displace. Okay, so if you have a volume, for example, a cube, side A, and you float it on water, it just floats there, okay? If you put a 1/3 of a mass, 1/3 of a mass on there, it will displace 1/3 mg of water. If you put 2/3, 2 bricks there, it'll displace 2/3 of mg of water, and you put them all there, it'll submerge the entire cube. So the buoyant force is going to be 1/3 of the weight of the water displaced, which is going to be the density times the volume times g. And the middle one is 2/3, and the final one is just rho g times the volume of water displaced, which is the volume of the cube, which is a cube. So that's buoyancy. And then finally here is Bernoulli's principle. Now, Bernoulli is really just took energy conservation, which you already know about, gravitational potential energy, kinetic energy, and work. And he took these 3 terms, which he knew to be energy, and he simply wrote down the conservation equation for these 3 quantities in a fluid. And it could be air or water, any fluid you like. So what was his formula? Well, the energy is equal to the gravitational potential energy of the fluid. In other words, how high the fluid is, the altitude, okay? Plus the kinetic energy of the fluid. What's the velocity? In other words, wind velocity or water velocity. Plus the work that the fluid does. And the work that the fluid does is actually the force times the distance. It's the same like we had a friction force over a skid distance. Well, this is the force of the pressure. This is the pressure of the fluid times the distance through which the pressure works, and the force is the pressure times the area. So the pressure is a force per unit area, so a pressure times an area is a force. So it's a force times D. So he just wrote this down, and that's it. So now you can see that if these 3 terms, gravitational potential energy, kinetic energy, and work, if those three things have to always be a constant, that's what energy conservation is, the total amount of energy does not change. If these 3 things are a constant, and you neglect the height, for example, so there's not much altitude here, you can see that when v squared goes up, p has to go down, because the sum has to be a constant. Okay? That's it. That's Bernoulli's principle. If velocity goes up, pressure goes down. Now, we can illustrate this here with a balloon. And I think first off we'll look at the video and then look at the explanation, okay? So let me say also, by the way, I made a comment earlier that an airplane has lift because of Bernoulli's principle. The air goes over the top is going faster, pressure is lower, low pressure on the bottom, low pressure on the top, big pressure on the bottom, and the wing lifts up. Well, this is not a complete explanation, by the way. I mean, if you ask an aeronautical engineer about that, they might just laugh, okay? Actually, the lift of an airplane is very complicated. I mean, Bernoulli's principle plays a role, but also vertical momentum conservation also plays a role, and so on. So it's very complicated, but in any case, Bernoulli's formula is very simple and easy to think of. So here's an illustration of when the velocity goes up, the pressure goes down. So let's take a look at this video here.
We're going to demonstrate Bernoulli's principle. Now, Bernoulli's principle is used to measure airspeed, and it is also responsible for airplanes flying, in the sense that they have an airfoil, a wing, And if the velocity of air on the top is higher than on the bottom, then the pressure is lower on the top than the bottom. And so the net pressure difference on the wing of an airplane is up. And that's called lift. That's why airplanes can fly. Okay? So we're going to demonstrate this with a hairdryer. It's just a simple hairdryer. And here's a balloon. I'll explain, read in the recorded lecture, a little bit more how this works, but just watch first. I'm just going to put it on low speed here. And okay, now observe what's happening. First off, the air pressure itself keeps it up. Secondly, whenever it fluctuates to the right, the pressure on the left is lower and it goes back again, and vice versa. So what it's doing is doing a very gentle oscillation. When it goes too far this way, the pressure pushes it back, and then the pressure reverses, it pushes it back again. And so this balloon is doing an oscillation. Now, it's not like the very nice oscillation of your mass on a spring. That's called simple harmonic motion. This is not simple harmonic. It's more jerky, but it is an oscillation, and that's Bernoulli's principle. If I turn it off, it will just come down. Okay? Now, it should work for every mass. Ping pong ball. Ready? This one requires more velocity. It's smaller, so it's more airflow to keep it up. So let's see what we've got here. Now let's see, how am I going to do that? Are you still going? Oh, shoot. Okay. Here we go. Go. So it's the same thing now. All right, just a different scale, that's all, but the same thing. And again, it's jerking back and forth. And, okay. It's now starting to spin. I don't know why exactly. Maybe there's a groove on one side. Very smooth, actually, but the jerky motion you can see is much smaller than a balloon. Okay, the balloon will go like 10% of its width, and this thing is also going to like 10% or 5% of its width. So that's Bernoulli. Okay? Bernoulli, and I'll explain this more with pictures in the recorded lecture. Okay? There we go. All right.
Well, here's a drawing then of a balloon. And here's an air dryer. It's held fixed at the bottom and has a rather narrow chute, I think, actually. And as the balloon goes to the left, then the air velocity going around the right-hand side is higher because it kind of shoots straight up. The air going around the left-hand side is lower velocity because it has to go farther out, and there's probably even less air there to boot, okay? So the pressure on the right-hand side of this balloon goes down. The pressure on the left is still the same, basically. So the net force is to the right. So then the balloon shoots to the right, and now it finds itself in the reverse situation, okay? With low pressure on the left, high pressure on the right, and it goes back again. So this leads to this kind of a jerky oscillation of the balloon. And then here's a photograph of just the ping pong ball. This hair dryer that I have in the lab actually is a little more powerful than the one at home here, right? So you can adjust the airflow. It's better, I think, to have a narrow chute here rather than a broad chute of air. Okay. Now, Bernoulli's principle also works. For example, you can blow across the 3x5 card. Take a 3x5 card and put it on anything, a cup or a glass or something, and then you just blow across the top, just with your mouth. You blow across the top, or you can actually blow through a tube. Actually, maybe you can use the PVC tube. Blow air across the top. That lowers the pressure on the top. Pressure on the bottom stays the same, and there's a net lift, so the card will actually lift up. Okay, so that's a simple Bernoulli, not as dramatic as the balloon, but quite good. Now, let's see here. Let's see. Here is. Hello, I just didn't include I didn't download a video here. This is, now why did I miss it? Let's see, why did I miss it? I missed it here because, okay, here we go. I missed it here when we were talking about the weight of air. I don't know why. Here we go.
In this segment, we're going to actually weigh the mass of air. In other words, the stuff that's right here, we're going to weigh it with our fantastic little 0.01 gram electronic balance. So we're going to do it this way. Here's a balloon. I'll weigh the balloon with no air in it. Then I'll fill it up with air. Weigh it again. That's all we're going to do. Simple as that. Now, to make it easy, when the balloon is blown up, it's like this big and it has to balance on here, and we don't want it to touch the sides or something. So I'm going to put a little scotch tape, your scotch tape here, that will hold the balloon in place. So I'm just going to do it like double-sided. That's all. It just doesn't need much, just a little bit. Oops, I should have made it bigger. Yikes. Okay. I guess that'll do. Okay. And so now let's turn it on. And so the scotch tape is on here, but whatever mass is on here, when you start it up, it starts out at 0. So it's 0. So let's now just weigh the balloon itself. Okay. And I see 2.73 grams. So I'm going to record here, empty balloon, 2.73 grams. Okay, now let's blow it up. Okay, off, just like a birthday party. Okay. Now we're going to take another look. I have to get up to read it. I think we should wait until it settles down. Okay, 2.82, 2.84, 2.84. Okay, so it's settled down at 2.86, 2.84. I'm going to call it 2.85. 2.85 grams. Okay? Now, what I'll do off camera is calculate, well, you see the difference in, it's heavier by 0.12 grams. So off camera, what I'll do is I'll estimate the volume, and I'm going to assume it's a sphere, and then I'll put the ruler up here, and just do an eye estimate. This is not going to be very precise. I'm just going to say, well, it looks like it has a diameter of about 20 centimeters. So the radius is 10 centimeters, and the volume is 4/3 pi r cubed. Okay, that's a formula for the volume of a sphere, 4/3 pi r cubed, where r is 10 centimeters. So then I'll calculate how many grams per cubic centimeter, how many grams of mass of air per cubic centimeter of air, and that will be the density of air. So I'll do that off camera and show you my little calculations, okay? So you see, actually, I'm very happy that that we put the electronic balance in the box, because this thing is useful in many, many different ways. Okay, see you in a minute.
Okay, here's the mass of balloon by itself, 2.73 grams. Mass of air plus balloon is 2.85. So the difference is like 1/10 of a gram. Now the volume turns out to be about 4 liters, actually, 4,000 cubic centimeters. So the density came out to be 0.03 grams per cubic centimeter, which, by the way, is way too low. I don't know why. I did this again, and I got slightly more reasonable result, and so on. I don't know whether it's the balance, whether it's the carbon dioxide or water vapor, because when you blow a balloon up with your lungs, it has water vapor in there and some carbon dioxide, which are lighter than air, by the way. So I don't know, but the air is heavier. Okay, so I want to just leave it at that. The air is heavier. Okay, so finally, let's discuss activities for this week. First off, definitely measure the focal length of those two lenses. I mean, even put for example, your cell phone light on the other side of the room, and actually, if you want to, you turn off the lights in the room, make it easy, and then see the distance from the wall or from a piece of paper, the distance that the lens is to get a focus, and then just measure the focal length. We got a nice ruler here, okay? And then form an image of a lighted object on a piece of paper with a converging lens. In other words, put an object close by, put the lens in between until you get a good image, an image on a piece of paper, for example. And then make a simple microscope just to see. In fact, you might put the ruler down and try to see what your magnification you can get with these two simple, cheap lenses. Activities with heat, well, the only one is to ruin a butter knife in your home. Temperature at one end and see how long it takes to go. Like I said, it took me 12 minutes for even one end to even get warm, not even hot. And I had the flame going on the other end all the time. Now with fluids, I would do both the balloon and the ping pong ball, or with a hair blower, with any kind of blower. Okay, and also try to measure the mass of air if you can by the same technique. And I think one should have one of those little plastic little pumps for balloons. I think would work better than blowing it up yourself. But anyway, so that's it, and I'll see you Monday afternoon, 3:20, to discuss any of this. Ask any questions. There's a chat box. You don't have to speak up. If you're too shy to speak up, just put your question in the chat box, and we'll go from there. All right. Bye.